Question 5 is a question about specific heat capacity and power. Some parts of this question are pretty tough. 5.1 though, basically you have to suggest how the student that was conducting this experiment was able to ensure that the change in temperature was the same for each mass of water. So quite a tough start to this question. Well, the key thing to remember here is that water always boils at the same point, 100 degrees, and that would get you a mark. The second mark is for realising, well, therefore, all we need to do to ensure the same change in temperature is to control the starting temperature. And you could do this by basically allowing time for the water in the kettle to reach room temperature, which should be pretty constant. So, water always boils. At the same temperature each time, and for the second mark, therefore control the start temperature by allowing time for the water and kettle to reach room temperature. We'll come back to this table of data shortly, as it's going to be used in the next few questions. Five 5.2 asks you to calculate the uncertainty in the student's measurements of time to boil when the mass of water was 1.75 kilograms. Well, if we go back to the table, at 1.75 kilograms, we need to take into account the range here. Now, the smallest value they got was 298 seconds, the highest was 302 seconds. So to calculate the uncertainty, we need that range. So 302 minus 298, that would give us a range of 4. But we're not being asked for the range, we're being asked for the uncertainty. And to calculate uncertainty, it is the range, divide that by 2, and that'll give you an answer of 2 seconds. Now, an uncertainty needs to be written as plus or minus 2 seconds. So that is our uncertainty in our readings, plus or minus 2 seconds. 5.3 requires you to do a calculation to calculate the electrical energy used by the kettle in kilojoules. Very important, for the 1.75 kilograms of water to reach boiling point. You're told the power of the kettle is 2.20 kilowatts. So, first thing we need to consider is what mathematical relationship do we need to use. You'll need to recall that energy is equal to power times by time. Now, there is no need to convert the 2.2 kilowatts into watts here because we're after an answer in kilojoules, so we may as well stay with the prefix of kilo throughout and we'll get the right answer straight away. So 2.2. Now the time required, well, you're going to have worked out the mean or calculate the mean that's been left out of the table here. The mean for this is 300. Add these 3 up, divide by 3. The mean is 300, and that's the value you will need to use. Put that into your calculator and you'll get 660 kilojoules. So that is the amount of electrical energy required, and for the sake of completion You could even fill it in the table there. 5.4 then is asking you to work out the change in temperature of the water during that investigation. For this, you need to take into account then the mass, the change in temperature, the mass times the change in temperature bit, and if you divide that by mass, well, you end up left with the change in temperature. So we need to use the information from table 2 to do this. So we've already got a mass times change in temperature here. So we can pick any value, we can just pick the first value for example. So that mass times change in temperature is 20. Now if we divide that by the mass used in the water, 0.25, that'll leave us with the change in temperature left. So essentially we're dividing mass by mass to cancel them out. So to do the full work of this, mass times change in temperature, I'll just abbreviate, divided by the mass. So for example, therefore that would be these points, 20 divided by 0.25, put that in your calculator and you'll get a change in temperature of 80 degrees. You could use any row in the table, I just picked the first row there, you'd get the same answer every time. Okay, 5.1 then requires you to study a graph. So the student plotted a graph of energy supplied in kilojoules against mass times change in temperature in kilogram degree centigrade. And there's the graph the student plotted. There are 4 missing points from it still, and these need completing using the data from table 2. So we've got the 80 value, which needs completing. Let's bring the table alongside. The 80 value for mass times change in temperature, the energy supplied is 401. So it's just there. 100 is 471, which is there. 120 is 587. I'll do there. And the final one, 140, calculated it earlier, is 660. Now, for the next part, we're then being asked to draw a line of best fit. And for that, you need to make sure you use your ruler for this. By drawing a by drawing a line without a ruler, you will not be able to get the marks for this. So, line of best fit, somewhere around there would suffice. A fair number of points either side of the line, and to the axis there. That would be. So there was 3 marks for this in total. You would get 2 marks for the 4 points plotted correctly, and an accurate line of best fit would get you the 3rd mark for that. So 5.6 is quite a tough question. You have to use the graph now to determine the mean value of the specific heat capacity of water for the student's investigation. For this, you need to use the gradient of the line of best fit you've just drawn. You will see if we look back at the graph that we've got energy against mass times change in temperature. Now, from the specific heat capacity equation, the specific heat capacity is equal to energy divided by the mass times the change in temperature. So the gradient should give us the actual specific heat capacity. So let's get some values then. Try and make a bigger triangle as possible with this. So let's choose, well, with this we'll stick with a known point. We'll stick with there. So the change in y value for that should be the 587. For the sake of argument, we'll call it 580. Now the x value change is 120. Now, this isn't true that it is exactly 580, and is a common mistake made by students in the fact that here this doesn't go all the way down to 0, and so in fact this would be an extra 40 to take off. So in fact this is 540. So we can now calculate the gradient of the line from that. You get a mark for correctly reading some values. You get a mark for converting to joules, because you'll remember here again we're in kilojoules here. We won't get a correct value of specific heat capacity for this. So currently we've got an energy of 540 kilojoules, so that will need to be 540,000 joules. We've got an M times change in temperature value of 120. So to find the gradient, 540,000 divided by 120. Put that into your calculator, and the examiner in this case would be expecting an answer somewhere between 4,200 and 4,800. So quite a leeway there. As long as your value is in there, you've done the working, you've shown the points, and you've correctly converted it, you would get all 4 marks. 5.7. The value of the specific heat capacity the student got was greater than the accepted value. Suggest why? Well, some of the energy supplied by the element in the kettle will not actually go into increasing the temperature of the water. Some energy will be wasted, some energy will be wasted to the surroundings. So as long as you can suggest something along those lines, you would get the mark. So some of the energy supplied does not raise the temperature of the water. You could say some energy is wasted. Finally, 5.8. Again, for 1 mark. The kettle used in the experiment has a label stating that the power rating of the kettle was 2.2 kilowatts. The student did not measure the power of the kettle. Suggest why measuring the power of the kettle may improve the student's investigation. Well, the key point here is, although the power rating on the kettle states 2.2 kilowatts, the kettle may not actually be delivering 2.2 kilowatts. So if the student actually measured it, then they could probably accurately calculate the amount of energy supplied to each unit mass of water. So something along these lines should get you the mark. Power may not be 2.2 kilowatts. Student can accurately calculate the amount of energy supplied if they measure the power.